The research proposes the utility of an existing metric, deviation from stochasticity, DS, measure to characterize resting state fMRI time series for Alzheimer's disease, AD, classification. An autoencoder-based model is used to learn efficient representations of fMRI time series data. The methodology is applied on fMRI time series of 50 healthy individuals and 50 subjects with AD, obtained from the ADNI database. The study aims to create an efficient diagnostic technique for AD classification by analyzing the structural disparities in fMRI time series of the default mode network, DMN. The DS measure is applied to identify significant differences in the level of structure between healthy and AD subjects, achieving a peak classification accuracy of 95% using a gradient boosting classifier. This approach has the potential to provide a novel biomarker for AD classification, leveraging the strengths of fMRI and machine learning techniques. The research focuses on diagnosing Alzheimer's disease, AD, using the deviation from stochasticity, DS, measure in resting state functional magnetic resonance imaging, RS-fMRI, data. The approach involves analyzing the brain's default mode network, DMN, for significant changes or varying patterns that contribute to disease classification. The study utilizes a novel method to quantify the deviation from stochasticity in RS-fMRI time series, aiming to classify subjects into healthy and AD-affected groups based on the DS metric. The methodology includes loading and preprocessing of fMRI data from the Alzheimer's Disease Neuroimaging Initiative, ADNI, database, focusing on the DMN regions. The DS measure is applied to identify the deviation from stochastic behavior in the time series of brain regions, allowing for the classification of subjects and the identification of significant regions of interest contributing to the disease. The proposed method is designed to overcome the limitations of existing techniques by providing a more accurate and robust classification approach. Here is a combined summary of pages 58 of the research paper. The preprocessing steps for functional magnetic resonance imaging, fMRI, data involve motion correction, artifact removal, intensity normalization, and smoothing. Spatial normalization is performed to align individual brain images with the Montreal Neurological Institute (MNI) template. The default mode network (DMN) is parcellated into 160 regions of interest (ROIs), using the Dozenbach atlas, and time series are extracted from each ROI. Stochasticity in fMRI time series is identified using statistical measures such as variance, standard deviation, and autocorrelation coefficients. An autoencoder-based time invariant representation is used to measure deviation from stochasticity, DS, in fMRI time series. The DS metric is calculated by computing the window-wise bias from the input time series signal. Adding this bias to the dissimilarity curve, computing KL divergence between the input time series signal and bias-corrected dissimilarity curve, and calculating the coefficient of variation. The study compares the DS values between healthy and affected individuals, observing consistent trends within each class, and among different ROIs, observing variations in the DMN. The investigation reveals significant changes in DS values between symmetrical ROIs in both healthy control and Alzheimer's disease classes, helping identify the main regions deviating from stochasticity. An ablation study is conducted, computing coefficients of variation for each subject, which shows significant differences between healthy control and Alzheimer's disease subjects. Classifiers, including support vector machine and gradient boosting, achieve high accuracies for covariance-based classification of subjects. Shapley additive explanations is applied to explain the internals of the classifier, assigning importance values to each feature. The study confirms the nodes contributing to Alzheimer's disease versus healthy control classification and plots the DS values among the healthy control and Alzheimer's disease groups corresponding to the ROIs, observing a consistent pattern in healthy controls and an abrupt pattern in the Alzheimer's disease group. The research utilizes the deviation from stochasticity, DS, metric to identify disparities in time points of fMRI data, enabling the classification of individuals into healthy controls and those affected by Alzheimer's disease, AD. This approach offers a novel method with high accuracy for AD classification. Machine learning models, such as Random Forest Classifier, RFC, and gradient boosting classifier, GBC, are incorporated for subject classification. The results demonstrate a high accuracy of 95% in classifying subjects using the DS metric, highlighting its potential for clinical applications. The paper also reviews various studies and methodologies related to fMRI data analysis, emphasizing the importance of understanding brain function in disorders.